So now we're going to take a look at a more generic summation. We're going to take the sum of I from I equals 1 to n. What that means is I'm going to take 1 plus 2 plus 3 plus all of the numbers up to the nth number, the nth integer. But that's going to work the same way as before. We're going to pair them up. We're going to say that this one plus this one is 1 plus n. And we're going to say this one plus this one, that one right there being n minus 1, the number before n, is also going to be 1 plus n. And we're going to just see that we've got a whole bunch of different 1 plus n's. The question is, how many 1 plus n's do we have? Well, if we have n numbers total, then we're pairing them up. We're going to have half of that, or n over 2 pairs. So n over 2 times 1 plus n is going to give us the generic sum of the first n integers, n positive integers. And normally we'll write it like this. We'll write the n and the n plus 1 in the numerator and the 2 in the denominator. So that's a formula that we can use whenever we're taking the sum of some sort of linear progression. Like, for example, we just did this sum on the previous page. It was negative 2i plus 7 right here, from 1 to 23. We can just jump straight into the formula that we just used. We can realize that because we're adding up a whole bunch of terms, we can look at this like the sum from I equals 1 to 23 of all of my negative 2i's. And then I can also add up the sum from I equals 1 to 23 of all of my 7's. And if we think about this first sum right here, we've got negative 2i. We have got a factor of negative 2 for each term. So I'm going to go ahead and factor that out, and I'm going to factor out that negative 2, and I'm going to be left with the sum from I equals 1 to 23 of just plain old I. And then again, this is the sum from I equals 1 to 23 of 7. So how do we do this? Well, the negative 2 is just hanging out as a factor. The I, the first 23 integers, we're going to use this formula right here, and we're going to replace n with 23. So we have 23 times 24 divided by 2. And that's the first sum. That's my negative 2i from 1 to 23. Now I've got to do 7 from 1 to 23. But think about what that means. That says 7 plus 7 plus 7 plus 7 plus 7, and we've got 23 of them. So we're just going to say 7 times 23. So I'm just going to do a quick calculation here. I'm going to do 23 times negative 24 plus 7 times 23, and it's going to give me negative 391. And if we did everything correctly, that should match the answer up here, which is negative 17 times 23. Thankfully, we get negative 391 for both of those. So this is another way that we can deal with linear summations. So as we can now see, we're going to ask the question, what happens when the sequence isn't linear? In other words, if I take the sum of all of the I squareds. So for example, when I equals 1, we get 1, and when I equals 2, we get 2 squared, or 4. When I equals 3, we get 9, and when I equals 4, we get 16. And we can add these up, no problem. We're going to get, I guess we're going to get 30, aren't we? We can add up 4 plus 16 to get 20, and 1 plus 9 to get 10. But we can't really do that same trick of adding the first plus the last, right? Because it's not a linear progression. If we try that with this one, we're going to see that the numbers keep on getting more and more spread out. And I don't really feel like typing in all 8 of those numbers into the calculator or adding them by hand. So I'm going to pull out, either you can use, on, say, your TI Inspire, there's a template button next to the number 9 that looks like this. It's got the absolute value, and it's got a little curly bracket thing. This is your template button, and you can do all sorts of great things with this button. So I would recommend you explore that. But since I don't have an electronic copy of this calculator, I'm going to go ahead and use Desmos, which is pretty powerful as well. I'm going to type in to Desmos S-U-M for sum, and it automatically turns that into sigma notation. And we're going to go from 1 to 8, and it makes you use the index of n, so I'll just do n squared. And it tells us that's 204. So that's a pretty fast way to do this. So 204. And for this last one, I'm not going to list out the first 80 squares. I'm just going to go back to Desmos. I'm going to change my 8. I'm going to try to change my 8 to an 80. And I immediately get the answer 173,880. 173,880. And if you feel like it, you can check that by adding up the first 80 perfect squares, but I don't intend on doing that myself. So I guess the next question is, what if we don't know how many terms we have? We want that generic form. Well, there's a way to show that there's a formula, and you can prove this, but we're not going to spend time proving it. Instead, I'm just going to ask you to trust me on this. It's going to start off the same way as the i's. We're going to have n times n plus 1, but we're going to have a third factor. It's going to be 2n plus 1. And we're going to divide this not by 2, but by 6. So I'm just going to spend a quick second to verify that I'm remembering this formula correctly. I'm going to plug in 80 for n up here, and I'm going to get this product right here, and I'll type that into the calculator. I'm going to get 80 times 81 times 161 divided by 6, and thankfully I get the exact same answer that Desmos told me a second ago. So it sure does seem like this formula right here is legitimate. It's going to give us the sum of the first n perfect square integers. Alright, so what do we do now? Well, we've got one more formula to memorize after this. That's the cubes. So let's recap. If we're adding up c, where c is a constant, we're just going to take c times, well, how many c's do we have? We have n of them, so we're going to have c times n. If we have 1 plus 2 plus 3 plus 4, all the way up to n, we have that n times n plus 1 over 2 divided by 2. And with the I squareds, we just did that. We said n times n plus 1 times 2n plus 1, and we divided that by 6. One more time, we've got this I cubed here. That's going to be 4 factors in the numerator, but they're both repeated. It's the same 2 that we saw up here, but n squared and n plus 1 squared, and this time we're going to divide by 4. And again, I'm not going to prove those. I'm just going to ask you to trust me on those. But when we have those formulas, it's going to make it possible to evaluate something like this by breaking it up into pieces. So for example, I'm going to say this is the sum from I equals 1 to 10 of 2i cubed, and I can factor out that 2. I'm going to factor out the minus 3 here, and I'm going to have I squared. I'm going to factor out the 6 here, and I'm going to have I, and I'm going to, I guess I could factor out the 12. I might as well factor out the 12. I'll stay consistent, and I'll do I to equals 1 to 10 of just plain old 1, because 12 times 1 is 12. So when we work those out, we get 2 times, well, our cube formula tells us to take n squared and n plus 1 squared and divide that by 4. And then we've got minus 3 times, and our squared formula tells us to take n, which is 10, times n plus 1, which is 11, times 2n plus 1, which is 21, and we're going to divide that by 6. And then we've got 6 times our I formula is 10 times 11, n times n plus 1. Divide that by 2, and then finally we get negative 12 times 10. So negative 12 times 10. So we can work each one of these out. This is 121 followed by 2 zeros, and then divide that by 2. Okay, I'll just use a calculator for that. I was going to be brave and do it by hand, but I don't want to make a mistake. And it works out to be 60/50. This one works out to be 10 times 11 times 21, again divided by 2, and we get 1155. This one I think I can handle. This is going to be 330. And this one's going to be negative 120. So we take 650 minus 1155 plus 330 minus 120, and we get 5150. No, I'm sorry, 5105. And just to verify that, I typed it into Desmos, and lo and behold, we do get 5105. So that's a nice way to double check your work.